In this video, we are going to prove a statement related to a two-connected graph. So the statement reads as follows: if G has at least three vertices, the following are equivalent. Okay, that says G is connected. For any distinct vertices U, V, W in G, there is a path from U to V that does not contain W, and G is connected and has no cut vertex. So in order to prove the equivalence among these three statements, only need to prove a circular implication. Only need to prove statement 1 implies 2, 2 implies 3, and 3 implies 1. So if we are able to prove these three implications, then we can say that these three statements are mutually equivalent. So 1 is equivalent to 2, 2 is equivalent to 3, and 3 is equivalent to 1. Okay, so let's prove each one by one. So let's prove this statement 1 implies 2. So 1 implies 2 reads as follows. Okay, if G has at least 3 vertices and G is 2 connected, then for any distinct vertices U, V, W in G, there is a path from U to V that does not contain W. Okay, so let's go and prove that implication. Okay, so we are given that G is connected and G has at least 3 vertices. So using that, we are going to prove that for any distinct vertices U, V, W in G, there is a path from U to V that does not contain W. Okay, so since G is 2 connected, so we are given that G is 2 connected. So since G is 2 connected, removing one vertex, it won't delete, it won't disconnect the graph. We need to delete at least 2 vertices to make this graph disconnected, since the graph is 2 connected. Okay, so since G is 2 connected, and if you remove a vertex, say W, G with W removed is a connected graph. G with W removed is a connected graph. Again, let's call that graph G dash. Okay, so G dash, it is equal to that G minus W. And again we can see that G dash is also connected because we are dealing our original graph G is a 2 connected graph. Thus G dash is a connected graph. So that says if you consider any 2 vertices U and V, there will be a path from U to V in G dash. Again, this G dash is obtained from G, and we can see that by deleting this vertex W. So since there is a path from U to V in G dash, that path, it does not contain this W because we obtained G dash by removing this W, right? And again, if you look at our original graph G, that graph is also connected. So the same path, it must exist in G. And that path, it is not going to contain this vertex W. And that's what we want to prove. So let me write down what I said. So in G dash, since it is connected, there is a path from U to V, which in G is also a path from U to V, but without using W. And that's what we want to prove, right? So if G is 2 connected, then for any distinct vertices U, V and W in G, so there is a path from U to V that does not contain W. Okay, so since the graph is 2 connected, we need to remove at least 2 vertices to get the graph disconnected. So let's delete this vertex W. Okay, and obtain this graph G dash. And since G is 2 connected, G dash is also a connected graph. So there exists a UV path. Okay, without using this W. Okay, and okay, since we obtain this G dash from G by removing W, same path must exist in the original graph also, and we can see that that path, it does not contain this W. Okay, and that's it, and we proved that implication 1 implies 2. So if G is connected, then for any distinct vertices U, V, W in G, there is a path from U to V that does not contain W. Okay, so let's go and prove 2 implies 3. So the 2 implies 3 reads as follows. So G has at least 3 vertices, and for any distinct vertices U, V, W in G, okay, there is a path from U to V that does not contain W. Okay, then G is connected and has no cut vertex. Okay, so let's go and prove that. So using this, we are going to prove that that graph G is connected and has no cuts. So we will start with the graph having this property. Okay, then we will use this contradiction to come up with okay, this thing. Okay, G must be connected and has no cut vertex. Okay, so let's go and prove that statement. Okay, so let G has that particular property. This property 2. Okay, so that says G has at least 3 vertices, and for any distinct vertices U, V, W in G, there is a path from U to V that does not contain W. Okay, so let G has property 2. So let's say, okay, again we can see that for any distinct vertices U and V, there is a path from U to V. So that says G is connected. Okay, so we proved this part G is connected. Okay, so okay, since it satisfies property 2, okay, then this graph G is connected. So we need to prove that it has no cut vertex. So we will start with, so that we are going to prove that part by contradiction. So we will start with a cut vertex and we will arrive at a contradiction. Okay, so let's see how okay that can be done. Okay, and suppose that it has a cut vertex, and let's call that cut vertex W. Okay, suppose that this vertex W is a cut vertex, okay, of G, and let G double dash is a graph obtained after deleting this cut vertex W. Okay, since W is a cut vertex, G double dash is a disconnected graph. So it has 2 components. Okay, it has at least 2 components, and okay, let's look into those 2 components and see what is going to happen. So it has at least 2 components, and let U and U and V be 2 vertices into different connected components. Okay, we know that G dash is disconnected, so there will be at least 2 connected components. Okay, and let U and V, okay, U and V be vertices in 2 different connected components. Okay, in G double dash. Okay, so since U and V are in 2 different connected components in G double dash, okay, there is no path from U to V in G double dash. Okay, and since if you go back to our original graph G, okay, in that case, since that graph is connected, okay, there is a UV path. Okay, and in G double dash such a path does not exist because of the removal of that W. Okay, so that says in G, okay, every UV path must go through that vertex W. Okay, and that is going to be a contradiction. So we started with something like this. There is a path from G to V that does not contain W, and since we are, okay, if you assume something like this, W is a cut vertex, okay, then we will arrive at that contradiction. Okay, so let me write down what I said. Two different components in G double dash. Okay, so there is no path from U to V in G double dash. Okay, so if we go back to our previous graph G, it is connected and there is a UV path, and that UV path must go through that W. Okay, then every path joining these vertices U to V in the original graph G must use the vertex W. Okay, and that is a contradiction. Okay, so that is a contradiction because we assume that for any distinct vertices U, V and W in G, there is a path from U to V that does not contain W. Okay, and we arrived at that contradiction because of this assumption. Okay, we started with assuming that W is a cut vertex of G. Okay, and since we arrive at a contradiction, the W is not a cut vertex, and that says okay, G has no cut vertex. Okay, and therefore this G has no cut vertex. So if it has a cut vertex, then we arrive at this contradiction. Okay, so let's go and prove 3 in place 1. Okay, so that reads as follows. Okay, if G has these 3 vertices and G is connected and has no cut vertex, then G is 2 connected. So we need to prove that we need to remove at least 2 vertices to get the graph disconnected. Okay, so let's go and prove that. Okay, so since G has at least 3 vertices, and has no cut vertex, so we can see that okay, its connectivity is at least 2. Its connectivity is at least 2. Okay, since he has at least 3 vertices and no cut vertex, so that says its connectivity is at least 2. Okay, so that says it is 2 connected by definition. Okay, so G is 2 connected by definition. Okay, so that's it. So we are able to prove okay, those 3 implications. 1 implies 2, 2 implies 3 and 3 implies 1. Okay, so that says if G has at least 3 vertices, the following are equivalent. G is 2 connected. For any distinct vertices U, V, W in G, there is a path from U to V that does not contain W, and G is connected and has no cut vertex.